Hi there and welcome back. Now in this video we'll be doing a lot of problems regarding the head loss using the equations or the Moody diagram. Okay, so for our first problem, it's taken from the textbook by Mott and Turner. That's example 8.4. So for the problem, it says here, determine the head loss if glycerin at 25 degrees Celsius flows 30 meters through a standard DN 150 mm Schedule 80 pipe with an average velocity of 4 meters per second. The data for the density and viscosity is also given. Okay, so this is one of the standard specifications for pipes, or they're actually for example, there's also standards for example ASTM or AISI or whatever. Okay, so it's just one of the many specifications that's available out there. You can see here 150 mm, and this is the diameter, and the schedule refers to the thickness. Okay, so basically, if we have this and we have this schedule 80, then if there are tables available for the example inside diameter of the pipe or the outside diameter, then that would be more precise as to just assume that this is the diameter. Okay, because as we have mentioned before, that we're actually into the inside diameter. I mean, if it's available, if we can solve for the inside diameter, then that's fine. But if not, then I think for computations purposes, I think it's just okay. Okay, so now the first step, okay, for the solution, the first step is, if we have these kind of problems to solve for the head loss, and of course if that's head loss, then that means we're going to solve that using the Darcy-Weisbach equation. And recall that in order to solve for the head loss, we need to find the friction factor, and in order to find the friction factor, we need to find we need to determine if the flow is laminar or turbulent. So therefore, for the first step, solve for the Reynolds number. So Reynolds number is just equal to the velocity times the density times the characteristic length of the pipe, of the geometry, and for a circular pipe is just equal to the diameter. So if we substitute all the values, we have 4.0 meters per second squared times the density of 1258 times the characteristic length. If this is in millimeters, we have to convert that to meters. Okay, so I'm going to do that for the units, and this one is 9.6 times 10 to the negative 1. Okay, and that's gonna be 767. Therefore, since RE is less than 2000 or 2300, depending upon our reference text, then therefore the flow is laminar. So if the flow is laminar, then therefore right, let's write it here. If the flow is laminar, it means that the friction factor is equal to 64 all over the Reynolds number. So 64 all over RE, 767, and that's equal to 0.0835. Right, this is our friction factor. The third step is, okay, so solve for the head loss. So head loss in this Darcy-Weisbach equation is F L over D times the velocity head. So what is our F? That's 0.0835 times our length of 30 meters. So 30 meters divided by the diameter in meters, right, times the velocity, 4 meters squared all over 2 times the gravitational acceleration. And therefore, this will be equal to 13.96 meters. Okay, so again, if we do a recap on our procedure, we first solve for the Reynolds number to determine whether the flow is laminar or not. So once we know the condition of the flow, then we can select appropriate friction factor equations. Now this equation only works if the flow is laminar. If it's not, then you have to use the appropriate equation, known as the modified Colebrook equation. So now, since we have the friction factor, then we can solve for the head loss. Okay, now we'll solve another problem for this head loss. Okay, the next problem is compute the head loss and pressure drop in 80 meters of horizontal 150 mm diameter asphalted cast iron pipe carrying water at 20 degrees C with a mean velocity of 1.83 meters per second. Okay, and this problem is taken from the textbook by Gillissen. That's problem 7-34. Okay, so we are I have also attached here the values of the kinematic viscosity and the surface roughness. Okay, so if in case the problem doesn't give you any of these properties, then you can just obtain this from the tables or the textbooks. So you just have to find the fluid at that specific temperature. Okay, so for this is the kinematic viscosity, 1.005 meters squared per second, and this one is the surface roughness of 0.12. Okay, so 0.12 millimeters. I'll use the equation for finding F. So we can actually find F using the Moody diagram, but for now we'll just use the equations. Okay, so for that solution, so again, the first step is to solve for the Reynolds number. So RE is equal to velocity times the mass density times the characteristic length divided by the viscosity, right? However, what's given is the kinematic viscosity, and therefore our Reynolds number equation would be VLC all over this one mu. Okay, and therefore if we substitute all the values, our velocity is 1.83 times the characteristic length. Okay, so in 80 meters of horizontal 150 mm. So our characteristic length for the circular pipe is just the diameter itself. So this one will be 0.15 all over the kinematic viscosity. And that's 1.83 times 0.15 divided by 1.005. And I guess we're missing something. This one should be times 10 to the negative 6, and therefore this one should be times 10 to the negative 6. Okay, so 1.83 times 0.15 divided by 1.005 to the negative 6, and that's 273,134. Okay, and if we compare this, Reynolds number is greater than 4,000. So therefore, flow is turbulent. So therefore, our equation for the friction, okay, therefore F friction equation is F is equal to, or actually that's 1 over square root of F is equal to negative 1.8 log of the surface roughness divided by, or the ratio, actually the ratio of the surface roughness, the diameter is called the relative roughness. It's 1.11 all over 3.7 plus 6.9 all over the Reynolds number. Okay. And therefore F is equal to, if you do the math, what you get is 0.0197. Okay, so take note that this is F, but in our equation what's given is 1 over square root of F. So once you have solved for the you have solved this right hand side, then just do the algebra for extracting the F from this denominator and from this square root sign. Okay, so that's it. Now we have the F, and therefore for the head loss, that's going to be FL over D times V squared all over 2G. Our F 0.0197, and our L is 80 meters divided by the diameter of the pipe, that's 0.15 meters, times the velocity head, 1.83, right, squared all over 2 times 9.81. And what you will get here is 1.82 meters. And therefore, if in terms of the pressure drop, right, so in terms of pressure drop, what we get is delta P. From the equation, delta P is equal to the unit weight of the fluid times the head loss, right? That's the height of the head loss. So if in terms of pressure drop, then we'll use this equation. Therefore, since this is water, then this is 9,000 or 9.81 or 9,810. That's Newton per meter cube times 1.83 meters. 9,810 times 1.83, and that's 17,952.3 pascals. This is HL. Okay, so just a recap on what we did. The first step is to solve for the Reynolds number and to determine if the flow is laminar or turbulent. And once you know the condition of the flow, then you can apply the appropriate friction equation. Okay, so we use this Colebrook modified Colebrook equation for if the flow is turbulent, and we have solved that F is equal to 0.0197, and because we have now the value of F, then we can substitute that to the in this Darcy-Weisbach equation, solve for the head loss. And once you have the head loss, you can convert that into pressure drop. by multiplying the head loss to the unit weight of the fluid, we get this value. Alright, now we will use the Moody diagram in finding the friction factor. Okay, so for that, we will have this problem. Determine the friction factor F if water at 160 degrees F is flowing at 30 feet per second in a 1-inch schedule 40 steel pipe. Or I guess I think it would be better if we just use the sample here in our reference text. So if we have a Reynolds number that's 6.7 times 10 to the 3 and our relative roughness is 150, then let's see if we can obtain this value. Okay, so you go first in this Moody diagram. Okay, so the Reynolds number is 6.7 times 10 to the 3. So this is our 10 to the 3, this is 10 to the 4, 10 to the 5. So 6.7, this should be this is number 6, right? This is 8, so therefore this one is 7, and the 6.7 would be somewhere right here. And now we will project a vertical line. So 6.7. Okay, so this is our 6.7, and let's make this darker. 6.7, and our relative roughness is 150, which is this line. And therefore our intersection point is somewhere right here. And to obtain the friction factor, we will from this point we will project it to the left. Okay, and that's going to be 0.04 okay, 1 2 3 4 5, so 0.042. Okay, so that's 0.04, so F is equal to 0.042. Okay, and in this textbook the value is 0.043. Okay, because that depends upon how you accurately find the intersection point. Okay, so that's for the first one. Now for the second one, we have this 1.6 times 10 to the 4, and our relative roughness is 2000, so let's find it. Okay, so 1.6 times 10 to the 4. Now you have to select the range. So this is 10 to the 4, and we are looking at 1.6. So if this is 2, this is 3, 4, therefore this one is this must be 1. Okay, so 1.6. so if this is 1, this is 2, then therefore 1.6 will be somewhere right here. Okay. Right, and for our relative roughness we have a value of 2000, so this is the relative roughness. And from this point, you project a line to the left. And that's around 0.0, that's I guess that's 0.06789.0229. Okay, so that's F. This F is equal to 0.029, right? So this is 25, this is 26, 27, 28, 29, 30. Right, and the book gives us the value of 0.028284. Okay, so once again, in order to find the friction factor, you can just actually use the equation or use the Moody chart. Okay, so once you find the friction factor, then you can actually substitute the value into the Darcy-Weisbach equation. Alright, now let's move on to our remaining topics in this chapter. So we have actually types of pipe problem. So types of pipe problems. What it means is that we can have, for example, the first one is we have the known, let's say, parameters, and this one is the and right here will be the unknown. Okay, so we can have a problem where the known parameters are Q, that's the flow rate. It's also possible to have the this one, the diameter, and also the relative roughness and the velocity. And what's unknown is the head loss. Okay, so let's say this is type 1 problem, and for the type 2 problem, we can have this one is given, the diameter, the surface roughness, the velocity, and the head loss, and then we are to find the flow rate. And for the third type of problem, we can have, given the flow rate, then to solve for the diameter. Okay, so we're here given with the flow rate, the surface roughness, the velocity, and the head loss, and then we are to find the diameter. And by the way, I guess this should be viscosity. This one should be also viscosity. This one should be viscosity. Okay, so you're given with this flow rate, the diameter, the surface roughness, and then the viscosity to find the head loss. Then for a type 2 problem, you have this, the diameter, this one, also this, and then the head loss to find the Q. Now for the third type of problem, you have the flow rate, the surface roughness, the viscosity, and then the head loss to find the diameter. And sometimes I think that this type 2 and this type 3 problem is more like an iterative approach. That means that you have to guess, for example, the friction factor or something, in order to solve, in order to obtain what we're looking for. However, I have included in our lecture handouts the equations provided by Sweeney and Jane, 1976. They have developed explicit formula, right, for or formulas relating F, the head loss, Q, and D. Okay, so our equation, this is our lecture, in our lecture handout. So we have this equation for head loss, and you have all the parameters inside here, and if you're looking for Q, then you just substitute all the values here if you have it, and then for finding D, then you also have it. And then just take note for these conditions, right? So this is only applicable for example Reynolds number, that's between 3000 and 3 times 10 to the 8, or the and also the relative roughness, that's 10 to the negative 6, that's in between, and then 10 to the negative 2. Okay, so when using empirical equations, you just have to take into consideration the condition. Okay, now that's our last topic for this chapter is the minor loss, in which we will discuss this in the next video.